Okay, well, welcome back. Don't freak out. The stuff I put on the board is just stuff that we did last time, just so we don't have to copy the whole thing over again, so we have where we were last time. So what we've been doing is we've been looking at these very general techniques for proving something about the generalization error of a learning algorithm. So given a certain amount of data, what can we say about its generalization error, how well it generalizes to new data, or equivalently, if we want a certain accuracy, how much data do we need to give it? So we proved a bound like this last time. So given M training examples with high probability, we showed that for every hypothesis in the space, if the hypothesis H is consistent, then we first proved a bound like this on the error for when H is when the hypothesis space is finite. And maybe we were somewhat happy with this result, but we were also fairly dissatisfied with it for two different reasons. One reason is that we were restricting to where the hypothesis space is finite, and the other one was because we're requiring that the hypotheses have to be consistent for it to be of interest. We're going to deal with both of those. Last time we started dealing with the first one, and I just want to emphasize, since based on some of the questions I got afterwards, I'm not sure it was entirely clear, that for the development we were doing more towards the end of the class, that applied to all hypothesis spaces, not just where it's finite. And in that case, we proved a bound like this in terms of the growth function, which we talked about last time, which again, we were looking at the number of possible behaviors on a finite sample, and the growth function, this one, is the worst case number of behaviors we can get for this hypothesis space on a sample of size m. Okay, so we talked about this bound. We didn't prove it. We will eventually prove something, not exactly that bound, but something similar along the same lines. And we talked about how there are these two cases. I didn't explain why this is true. I will in a minute. But there are basically these two cases where the growth function is the worst possible, meaning that you can get all 2 to the m behaviors on some sample of size m, or this nice case where the growth function is only a polynomial. And in that case, this kind of bound simplifies to something like d log m over m. Okay, so of particular interest is this exponent, and that exponent will turn out to be the VC dimension, which we talked about last time. Okay, towards the end. Okay, so that's a quick review of where we were. Any questions before pushing forward? Okay, so the reason to look at the VC dimension again is because it gives us a bound on the growth function. It gives us a way of getting a handle on the growth function, which in turn gives us a bound on the generalization error. So that connection that I keep alluding to over here follows from a beautiful combinatorial result, which is called Sauer's lemma. Okay, it has multiple names, but the most common name in the learning community is Sauer's lemma. It actually was discovered independently by, I'm not sure how many people, at least 2, maybe 3. So what Sauer's lemma says is, suppose we have a class of hypotheses H, and let's let D be the VC dimension of that class. Okay, and assume that the VC dimension is finite. The VC dimension can be infinite. It just means that for any m, we can get a shattered set of that size. So let D be the VC dimension. Then what Sauer's lemma says is that this growth function, meaning the number of possible behaviors on any set of size m with hypotheses in H, is at most the sum from I equals 0 to D, the VC dimension, of binomial coefficients, m choose I. Okay, so m choose I, this binomial coefficient, this is the number of ways of choosing I items from a set of size m. So if you take this set, you get the number of ways of choosing at most d items from a set of size m. We're not going to prove this lemma because I just don't have time, and it goes more into combinatorics than into learning. I want to focus on learning, but there are beautiful proofs of this. You can prove it by induction. I mean, you have to work. It's not obvious at all, but it's possible to prove by induction. And the reason it relates to this is because if you think about the binomial coefficients, this binomial coefficient, m choose I, is that you can actually write that as a polynomial in m of degree I. So if you add them all up, what you'll get is a polynomial of degree d in m. And in fact, it's often nice to actually have a nice clean bound on this. It's possible to prove that this whole thing is at most e m over d to the d. This is a bound that's commonly used in this area, where this assumes that m is at least d and d is at least 1. Okay, so Sauer's lemma refers to this inequality. And then this is a separate bound. Okay? So once you prove Sauer's lemma, then that gives us this result that we had over here. So basically it's saying this nice case really means that the VC dimension, d, is finite. That's what this case is. And the fact that it's a polynomial follows from Sauer's lemma. In the other case, where VC dimension is infinite, I'm using d for VC dimension, if it's infinite, then that means for any size m, we can find a shattered set, which exactly means that all 2 to the m behaviors are possible. So we get exactly this result for all m. So the reason there are only 2 cases is because VC dimension is either finite or infinite. And that's it. Okay? Yes?
Log of pi of 2m.
Yeah.
And then you say pi of 2m is this em to the d. So is that log of something to the d?
Correct. Okay, so let's go ahead and do it. Okay.
The log cancel out the exponent.
Okay, so what we get, if we plug in over here, is we will get something like, I'm going to ignore constants, but we'll get something like d log m over d, if we use that bound over there, and then all the same stuff for everything else. Okay, so now if you just ignore this log term, which doesn't have much effect, I mean, it has some, but we're theorists, so for us it doesn't have much effect. So what we're getting is that d, VC dimension, is acting as a complexity measure now. So now VC dimension, for all hypothesis spaces, not just the finite ones, acts as a complexity measure. Does that answer your question? Okay. So people okay with that? So VC dimension, according to a bound like this, is giving us, it's kind of giving us an upper bound on how many examples we need for learning. If you think about this bound enough, what it's telling us is that to get a certain accuracy, the number of examples that we need, it's enough for it to be linear in the VC dimension. That we need something like linear in VC dimension examples for learning to be possible in this particular sense that we've been describing. VC dimension also turns out to be a lower bound. And I don't have time to explain why it's a lower bound, but hopefully you can get some intuition of why VC dimension also gives us a lower bound on how much data you need for learning. For a set to be shattered, it means that all possible labelings of that set are possible. And so if the VC dimension is D, there's some set where all possible labelings exist. And if all labelings are possible, and you only see part of that set, let's say you only see half the examples, you have no idea what the labels should be on the other examples because all labelings are possible. It's completely unconstrained. So if you only see some, you don't know what the labels are on the others. So you can take that basic idea and prove a lower bound in terms of the VC dimension so that it's providing both an upper bound on how much data is enough for learning, like a sufficient condition for learning, and it's also providing a necessary condition for learning. Okay, yeah.
Just to clarify, so if we want to show how to set this dimension is D, then we only need to just find the one example of the set with cardinality D such that it can be shattered, not for all the sets with cardinality D.
Correct. Okay. That will give you a lower bound on the VC dimension. So like if you want to show the VC dimension is 5, you have to find a set of size 5 that's shattered. And yes, you're right. There only has to exist one. It doesn't have to be all of them. And then to show that it's at most 5, you need to show that every set of size 6 is not shattered. Yeah, so good. Very good point. Good. Other questions? Okay, so let's move on to this other thing that we didn't like about this, and which I've gotten a lot of questions about, like, why are we only thinking about consistent hypotheses? Okay, so finally let's move on beyond that to where there might not be a consistent hypothesis. I guess you could go ahead and start the projector up. I'm going to use the projector just a tiny bit, but they need warning to warm it up. So, all right. So there are all kinds of reasons. Oh, geez. I might use this time to erase. Okay. So there are all kinds of reasons why we might not expect to be able to find a hypothesis which is consistent in our class. I mean, one reason is that there might not be a functional relationship between the instances and the labels. So for instance, if you're doing weather prediction and you're trying to predict whether it will rain tomorrow based on today's weather conditions, there's some inherent randomness there, and you don't expect to be able to get perfect accuracy no matter what, no matter how good your predictor, no matter how much information you have. So, so how do we deal with those very realistic cases? So what we need to do is to extend our learning model. So we'll continue to have instances X, and they will also have labels Y. But now this label Y might not be a direct function of X. So earlier, we could get away with the distribution just generating X, and then the label automatically came along with it because it was just a function of X. So now instead, we'll suppose that we have a distribution D, which is over pairs XY. So now an example is generated as a pair according to this distribution D. And you can think about this, you can either think about this distribution D as generating these jointly as a pair, or equivalently, you can think about the distribution first generating X and then generating Y conditional on X as kind of a probabilistic function of X. You can think about it either way. So we need to extend some of our notions of learnability. Oh, I didn't. It's yeah. Oh, yeah. I'm not going to need it for a minute. Oh, you want to make sure it's working? Or?
Yeah, well, I mean, we lowered the screen. I thought you were ready for it. So.
But I gave you warning because you said you wanted warnings. But then I talked too slow. So, all right. Yeah. So how do we measure the goodness of a hypothesis? So again, we still have a hypothesis H, and what we're aiming for are hypotheses which make mistakes as rarely as possible, which give correct predictions as often as possible. So we're still measuring performance by whether H makes a mistake or not. So H makes a mistake if its prediction on X disagrees with the correct label Y. And to measure how good it is, we'll really just do exactly what we did before. We'll just measure the probability of making a mistake where now X and Y are generated jointly according to this distribution D. Yeah?
Something you said a minute ago about sampling. So you said there were a couple ways to view how this pair XY is sampled from the distribution. I imagine that in most circumstances we care about predicting the label given X, right? Like, so the function I'm trying to estimate is like, you know, the expected value of Y given X. So wouldn't that one distribution, you know, choosing X randomly and then Y conditional on that, isn't that sort of the more important way to look at it?
It depends on your application. Okay, yeah, so there are different learning problems here. So Seb said yesterday that he views classification and regression as the same, which, with all due respect to Seb, and he deserves a lot of respect, there's no question about that. I disagree with him on that. I think classification and regression are different, and it's important to know what your goal is. Okay, so one goal could be to try to estimate probabilities, like estimate the probability of Y given X. So that's not what we're doing here. Here, the goal is just to be correct as often as possible. If you're doing weather prediction, you probably do care about probabilities. But in other settings, I don't know, you know, like web applications or something, you might care more about just being correct. Okay, so we're just focusing on that problem, and much of what I'm saying generalizes anyway. Okay, so this is our measure of error. Like I said, it's really exactly the same as what we had before, just probability of making a mistake, where we're regarding Y as correct, although the notion of what's correct for a given X might vary from one sample to another. So the name of the game is that we're given a sample. I'm always looking for the eraser, and it's always right here. It's that we're given a training sample, and we're generally working with a hypothesis space, just as we were before, which basically means that we've decided on the kind of hypotheses that we want to use. We, being the humans, have decided on the kind of hypotheses that we want to be working with. And we're trying to find the best one. So we're given a random sample, just as before. But where these pairs are coming from this distribution, this joint distribution D. And our goal is to try to find a hypothesis in our space with minimum error. So what we want to do is we want to minimize the generalization error over the hypotheses in this space H. Okay, that's what we'd like to do. I'm just going to drop D usually when it's clear from context. Okay, so this is generalization error. Of course, we don't have direct access to the generalization error, but we do have a sample. So there's kind of an obvious approach that we can use here, which is just to look at the training error of the hypotheses, the number of mistakes on this training set that we're given, as a proxy for the generalization error, and to minimize that instead. Okay, so we can define the training error or the empirical error, which I'll write as error hat of H. And that's just the number of mistakes on the sample, which we can write out in this form as an average of these indicator variables. Okay, this just means, 1 if this is true, 0 otherwise. So 1 if a mistake on the ith example, 0 otherwise. So this is the training error or the empirical error. It's also called the empirical risk, but the term risk is a little bit more general than what we're talking about here. So you could call it empirical risk, but that refers to something a little bit more general. And then the idea is to minimize this instead. So to choose H hat, which is the hypothesis in our space that minimizes the training error. Very simple idea. So this approach is referred to as empirical risk minimization, or ERM. So you might hear that term, ERM. Okay? Not very deep. It's the way most learning algorithms work these days. One way or another, they try to minimize the training error. But how do we analyze it? How do we show that this simple idea actually leads to a hypothesis with small generalization error? Well, the approach that's typically taken is to try to prove that the training error will always be close to the generalization error for every hypothesis in the space. It's kind of analogous to it's actually exactly analogous to what we did before in the case of consistency, where we proved something for every hypothesis in the space. So the kind of thing we want to prove is a result that says, with high probability, so say with probability at least 1 minus delta, for every hypothesis in the space, the generalization error of any particular hypothesis is close to its training error. Okay, and importantly, the order of quantification is extremely important here. That we want to say with high probability this is true for all of the hypotheses simultaneously. It's very important, otherwise the results won't work. So if we can prove this kind of a result, then it's saying that the training error is always close to the generalization error, always within epsilon. So if you minimize the training error, we will also approximately be minimizing the generalization error. And so I won't give a proof of that, but you can prove that in like 3 lines. Saying that if you have this, then if you minimize training error, you'll also be very close to minimizing the generalization error. So if we can prove that, then this H hat, which minimizes training error, will also be within, say, 2 epsilon of the best hypothesis, which minimizes the generalization error. Okay? Does that make sense? Or maybe I should prove that.
Going to be for any m?
Oh, this means, yeah, so epsilon and delta are going to be related to m. So it's like, yeah, so I should have said want for sufficiently large m. This is true. Good point. Yeah.
Like if you make a more and more complex H, so like you can always get M right.
Well, it's going to.
Is there any validation sense in here, or is it purely training?
We're going to get results like the ones we had before, which are going to depend on the complexity of the hypotheses we're working. Okay. 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 So this is the kind of result we're aiming for. These kinds of results are called uniform convergence results. Convergence because the training error is converging to the generalization error. And uniform because we're aiming for a bound which is uniform for all of the hypotheses in the space. And you can see how this kind of result exactly generalizes what we had talked about before. We kept talking about this case where we said, for every hypothesis, if it's consistent, then the generalization error is low. Well, consistency just means that the training error is equal to 0. So another way of stating those is that if the training error is 0, then the generalization error is small, which is exactly what this is saying. Okay? Okay. So this is going to be our aim, how to prove these uniform convergence results. So how do we prove those? Well, as usual, we should start with the easiest case. The easiest case is where we're not working with a whole class of hypotheses, but we're just working with a single hypothesis. So we just have one hypothesis in our hand. It's got some generalization error, and we want to estimate it using the training error. Okay, so in that very simple case, what we have in our hands is the training error. The training error is the average of these indicator variables. And we can think of, and each one of these indicator variables is actually equal to, it's equal to 1 with probability. Well, the probability that this is 1 is exactly the probability of making a mistake, which is exactly the generalization error. And it's 0 otherwise. So really, these indicator variables, they're really just coin flips. We're really just flipping a coin m times and looking at the fraction of times that it comes up heads or 1. And the bias of the coin is exactly the generalization error, which we're trying to estimate. And so to answer this question, to show that this converges to that, we just need to think about coin flipping. How fast does the average of coin flips converge to the bias of the coin? Okay, so to answer that, there are many techniques, but certainly a favorite tool, a favorite technique are to use what are called Chernoff bounds. And we don't have time to go into a lot of detail on Chernoff bounds, but I do want to talk about them a little bit. So our goal is to answer this kind of, to prove something like this, but I want to step back and view things more abstractly. So more abstractly, we have a set of random variables. Okay, so just for a second, forget all this stuff. Just have a set of random variables, z1 through zm. They're independent, identically distributed. Let's say that they're each in 0, 1. Okay, so if you want, you can think of them as the outcomes of coin flips. So 1 for heads, 0 for tails. And let's let p be the expected value. They all have the same expected value because they're IID. And if we want to estimate p, the obvious thing to do is to take the average of these. Let me call that p hat. And then the question we're asking is, how far is p hat from p? So a favorite result for this is Hufting's inequality. Which says that the probability that p hat, this empirical average, is more than the actual expected value by epsilon. So if it's too large by epsilon, the probability of that is at most e to the minus 2 epsilon squared m. Okay? So it's saying that the probability of being larger by epsilon is going down exponentially fast in the sample M. Okay? And there's a corresponding bound for probability of it being too small. Okay, probability p hat being smaller by epsilon. I won't write it out, but it has exactly the same form. Or you actually can prove it as a corollary. So this gives us a way of analyzing how close air hat will be to air. People okay with that? Okay, so before moving on, before coming back to learning, I want to mention another tool, a kind of generalization of Hoeffding's inequality, which is often very useful, and in fact is going to be useful later today. So in Hoeffding's inequality, what we're doing is we're trying to prove, oh, I can write over here. What we're doing is we're looking at the average. Oof. Going through these pens like crazy. Okay, the average, we're looking at the average of these random variables, and we're trying to show that it converges to the expectation of the zi's, right? And the expectation of the individual zi's is also the same as the expected value of this average. I mean, this is just a slightly different way of writing it. What the result says, it's saying that this average with high probability converges to the expected value of the average. And when you write it in this way, it kind of gives you an idea for generalizing this. Because really, we can think of this as a function, some function of these random variables. In this case, the function that we're talking about happens to be the average, and we're trying to show that this function converges to the expected value of that function, or that average in this case. But you could imagine trying to prove a similar result of this kind for other functions f, and this turns out to be very powerful. Okay, so the result for doing that, I mean, I'm sure there's more than one, but one of the really standard ones is called Mcdermott's inequality. So let me pull that up. I did it as a slide just because there's a lot of writing, and just to save some of the writing. Can we dim the lights a little bit, or I don't know, lights teaching, lights, lights. Oh my God, there are like 10 choices up here. Okay, this is probably way too dark, but all right, woo, okay. This will only be for a minute. In the meantime, maybe somebody can tell me a better setting of the lights. Okay, so oh, thank you. Okay, right, so we have this function, f, just a general function of some m variables. Okay, those variables really could be anything. And we need to restrict this function f a little bit for this to be true. So what we're going to do is we're going to consider functions f, which when you change the value of one of the variables, the function itself only changes by a little bit. So in particular, if you change one of the variables zi in any way you want to, the most that f can change is by some constant ci. Okay, so this is, we're assuming all this. So, you know, just in symbols, this is saying if you take zi, change it to some other value zi prime, the function f itself can change by at most ci. So if you have that condition, and if now we have random variables z1 through zm, and these have to be independent, but they don't have to be identically distributed. So independent, but not necessarily identically distributed. Then we can prove this kind of convergence result. So we can show that the probability that the actual realized value of f exceeds its expectation by some amount epsilon is some bound over here. Like, don't even worry about what the bound is, but there's some bound you can prove in terms of all the relevant stuff on how far off f can be from its average. Expected value. Okay, so for instance, in the case we talked about over here, this function f is just the average of these variables, and we assume the variables are between 0 and 1. So if you change one of these variables in any way you want to, the most you can change the average is by 1 over m, right? If you just change one of these terms, and they're bounded between 0 and 1, the most you can change the average is by 1 over m. So CI is 1 over m, and if you plug in, you get exactly the same as Hoeffding's inequality. Okay, so that's Mcdermott. Are people okay? Because once I tell them I'm done, then I can't do the projector down again, and that's it. Good? Okay. Okay. So I'm done with the projector. Okay. Okay, so coming back over here to learning and Hoeffding's inequality. Let's see. Actually, you could lift the projector. Oh, it takes a minute. Oh, it doesn't. I feel so powerful. Let the projector go up. Okay, so to prove this kind of result over here, using Hoeffding's inequality, we don't need Mcdermott. Using Hoeffding's inequality, all we do is we let Zi in Hoeffding's inequality be equal to this indicator variable. Now again, h is fixed. Then P, the P that's over here, will be the expected value of Zi, which is just exactly the probability of making a mistake, as we already discussed. And P hat, if you work it out, will just be exactly the training error of H. And so what Hoeffding is giving us is that the probability that, well, you have to plug in and do a little bit of algebra, but what it's saying is that the probability that the training error, P hat, differs from the generalization error by more than epsilon is at most 2e to the minus 2 epsilon squared m. Okay, 2 because I'm doing this absolute value here. It doesn't really matter. Right? I guess it's, yeah. Okay, so that's just plugging in. So this says, not surprisingly, that the training error gets close to the generalization error for one particular hypothesis. So now, let's suppose that we're working, okay, so we did the case where the hypothesis space consists of one hypothesis. The next simplest case is where the hypothesis space is finite, where we actually are working with a finite hypothesis space, and we want to prove uniform convergence on that. Well, we have the techniques for doing that. We just want to bound the probability of this not happening. So this not happening means that there exists a hypothesis in the space such that its error, training error, differs from generalization error by more than epsilon. And we know how to deal with this. I mean, we talked about this before. This there exists statement is like a gigantic or. It's like, you know, this bad thing happens for the first hypothesis, or it happens for the second one, or the third one, and so on. And when you want to bound the probability of a big OR, we can just use union bound. So if we just use union bound like we did before, we'll just get the same individual bound for each hypothesis individually. And then when you add them up, we just get a factor of equal to the cardinality of the hypothesis space. All right, yeah.
Which was the case where we considered only one hypothesis?
What is the bound you get, or?
What is this one hypothesis? In which case did we use only one hypothesis?
Oh, if there's only one hypothesis, so then we're using Hoeffding's inequality. And we get the bound without the there exists and this.
And why is it one hypothesis in that case?
Well, we were just doing the analysis as if that one hypothesis was fixed. And as long as that one hypothesis is fixed, then you can just plug into Hoeffding's inequality. You just, H is fixed, so you define the random variables here to be whether the ith example has a mistake.
But how do we restrict H in that case?
How are we using the fact that there's only one hypothesis?
Yes.
Well, for instance, we're using it to define these random variables. Okay, so we're saying fix a particular hypothesis, one hypothesis, and then we can define the random variables in this way. And, we get independence. I mean, there are all these conditions you have to, not a lot, but a couple conditions that these random variables are independent, for instance, and that their expected value gives the right thing. Does it make sense? Okay. Okay, so one hypothesis is basically plugging into Hoeffding. For finite hypotheses, we can just use union bound. I realize I'm glossing over details, but I think they're straightforward to check. Okay, so once we have a bound like this, it tells us something. Okay, it's telling us that with probability, at least 1 minus delta, to get the delta statement over here, all we have to do is, set this whole thing to be equal to delta. Just let it be equal to delta and solve for epsilon. And if we do that, we're getting that with probability at least 1 minus delta, this inside thing is not true, which means for every hypothesis in our space, okay, the error of H, I'm going to write it and then I'm going to change it. Sorry, you probably hate when I do that, but okay, that this difference is at most, and I'll use big O to hide constants, something like log size of hypothesis space plus log 1 over delta over m. Okay, so all I did to get this was set this equal to delta and then solve for epsilon. That's how I did that. Okay? And this is, this is perfectly fine the way this is stated, but I'm just going to change it a little bit. I'm going to get rid of the absolute values. I mean, it's still true without the absolute values. It's just, if anything, weaker, but really the only case is this case in this direction. You don't, if the error is even better than you expected, it's like, great. It's like, why are we talking about this? So, and then I just want to take this training error and move it onto the other side. Okay, so write it like this. Okay? Okay, so I did it. This is the more typical way of writing this kind of a bound. And what is this telling us? It's saying you're given a certain amount of data. I should say that up here. So as usual, given M training examples. So we're given a certain amount of data. It's telling us that if we find a hypothesis with some training error, then its generalization error will be at most the training error that we observe plus this additional term over here. And what does this additional term depend on? Well, it depends on number of examples, and it depends on log of the size of the hypothesis space, which is our earlier complexity term that we talked about before. So now we finally have this bound that ties together, really ties together those three conditions that I keep talking about. It ties together how well we fit the data, how much data we have, and the complexity of the classifier that we're working with. This kind of bound also makes predictions about how generalization error will be affected by the complexity of the hypotheses that we're working with. Okay, so we can draw a little cartoon of the kind of behavior we expect from a bound like this. Now, of course, these bounds, they're just upper bounds. We're not smart enough to prove exact bounds. We just prove upper bounds, and then we go, oh, this predicts behavior, even though it's really an upper bound. But so I'm going to do the same thing. Okay, so we can make a little plot. So here's complexity of the hypotheses that we're working with. And here is error. So as we increase the complexity of the hypotheses we're working with, as you use more and more complex hypotheses, we expect to be able to minimize the training error better. We expect to be able to do a better job of driving the training error down, of fitting the training data. So as we increase the complexity of the hypotheses, we expect the training error to go down. So here's training error. Now, what about the generalization error? Well, at first, the training error is going down. This term is going down. So we expect the generalization error also to go down. But as we increase the complexity, which is measured by this, eventually we expect this to overwhelm the fit to the data. And so at some point, we expect this thing to start going up again, according to this bound. Of course, this bound also predicts the error will get bigger than 1 eventually, which it certainly won't, but still, roughly it's predicting, that's a terrible picture. Let me try that again. Maybe something like that. Okay? Yeah.
So why we expect the empirical error to go down as the complexity of the hypothesis increases?
Well, just, okay, so it's a cartoon. So, but just typically, if you use a more complex hypothesis, you expect to be able to fit the data better. You know, generally what's constraining you from fitting the data is that you're trying to find something simple.
So overfitting, something like overfitting.
Exactly. That's exactly what this is. This is overfitting. Okay, so this is an expression that qualitatively, I wouldn't say quantitatively, but qualitatively gives some explanation of overfitting. Yeah?
So is it kosher for me to think of the complexity of the hypothesis space or like the cardinality of that as proportional and monotonically related to the number of parameters?
I'm not a fan of number of parameters, but sure. Yeah. Well, you can. Yeah. I can't tell you how to think. I mean, it's like. But you know, some notion of. A lot of times it is number of parameters, or description length, or VC dimension. Yeah. Was it? Yeah.
So if we compare this bound with the previous bound, When H is consistent, which means the empirical risk is 0, then this bound is actually not as good as the first bound.
Right, because of that square root. Yeah. Yeah, this annoying square root. Okay, so that stuff with consistency, that was not a complete waste of time. Because in the case with consistency, is your name Faye? As Faye said, when it's consistent, the training error is 0. So if you plug into this bound, you get this square root, which is a lot worse than what we had before. The bound we had before with consistency was without the square root. But when you don't have consistency, you're kind of stuck with it. So that's why sometimes you state both bounds. It's worth stating both bounds. And it's for real. It has to do with, it has to do with things like, estimating the bias of a coin. When the bias of the coin is very close to 0 or 1, it's easier to estimate with less data than when it's close to a half. So that's why the square root comes in.
In terms of the VC dimension. So right now.
Yes, yes, yeah. So that's what we're going to do next. Yeah, one more, and then.
So you hinting at that this is also a lower bound in that case? So when there is error.
Well, it's certainly a lower bound in the case of coin flipping, but to port that over to learning, I don't know, I'd have to think about it, probably, Okay. Okay, so let's move on. So of course, we're still only dealing with finite hypothesis spaces. And I do want to talk about the case with infinite hypothesis spaces here. And also, we didn't give proofs before, and I'm hoping I'm going to have time to actually prove some bounds. Okay, so what if the hypothesis space is infinite? Well, we talked about some techniques for when the hypothesis space is infinite based on growth function and VC dimension. Those all can be used as complexity measures. But instead, what I would like to do is talk about another complexity measure, which is just this amazingly beautiful measure, I think. Yeah, I shouldn't build up expectations, right? Because then you're going to see it and go, that was okay. But so, okay, I can't help it. Just a really beautiful measure, and one of the really beautiful things about it is that it subsumes all of the others that we talked about. So if you prove stuff for this one measure, you get all of the others, maybe not for free, but with only a little bit more work. Okay, so let me start introducing it, and then we'll do more this afternoon. Okay, so what we're doing now is introducing another measure, complexity measure, and technique for proving uniform convergence results. So suppose we have a sample S, a labeled sample, as usual. Now the labels, I've been using labels which are 0 or 1. For what we're going to do now, it's just a lot more elegant if we use labels that are -1, +1, and makes the math nicer. It doesn't change anything substantively, just makes the math nicer. So in particular, that means hypotheses now map to -1, +1 as well. So a really basic question we can ask is, if we have a particular hypothesis, how well does it fit this sample? Well, of course, we can just use the training error, right? And the training error, as I said before, is the sum of indicator variables. So this is actually a measure of how badly it fits the data. And because we're using +1, -1, we can take this indicator variable and write it as 1 minus yi h of xi over 2. Okay, because this is +1, -1. So if they agree, this product is 1. If they disagree, it's -1. And so if you just do it in your head, the two cases, this is equal to this indicator variable. Which means that we can take this error and just with a little bit of algebra write it as something like this. Okay, where these are just constants, of course. But the thing that I want you to notice is this kind of average of products. It's sort of like a correlation that we get here. So the whole point of this is just to say that we're going to use this kind of a term to measure how good a hypothesis is. Okay? And it's just off by constants from the error. Okay, so that was step 1, or the first step anyway. Okay, so to measure how good one hypothesis is on that sample, we're going to use this average. So now let's say we have a class of hypotheses, H, and we want to know how well this class of hypotheses fits this data. Well, to measure how good it is, we really judge how good it is by how good the best one is, how well the best one fits the data. So we can measure how good this class is by just looking at the maximum we can get for this performance measure for any hypothesis in this space. Okay? Okay, so far it's just been like totally, boilerplate, standard, blah, blah, blah kind of stuff. But here comes the weird part. Suppose we now ask, how well can hypotheses in this space fit noise? How well can they fit labels that are generated entirely at random? So imagine an experiment now where we generate each label, and for some reason it's traditional to use sigma I for these labels, where each label is generated at random. So it's +1 with probability 1/2, and -1 with probability 1/2. These are called Rademacher variables. And then we can use these as labels. And we can say, well, for a particular labeling, this class fits those labels simply using this same measure that we had here, but where for the labels we use the sigma i's. And then if we want to know how well they fit on average, we just take expected value, where this expected value is with respect to the choice of these sigmas. Okay? It's kind of a weird thing to do, but why does it make sense? Why does it make sense? Well, if you're dealing with an extremely rich hypothesis space, then if you have a very rich set of hypotheses, then you expect that it should be able to fit practically anything. So even if the labels are random, you should be able to fit that random noise. Whereas if the hypothesis space is very constrained, you don't have a rich hypothesis space, then we expect this to be much smaller. If you give it random noise, it should have a hard time fitting that noise. Okay?
Where do xi come from? For a given S?
It's just given. So this is for just a given sample. For any sample, we define it. Okay, eventually it will be random, but okay. So let's see, maybe as a quick exercise, so if the hypothesis space consists of just a single hypothesis, then what will the value of this be? Sorry? Yeah, it'll be 0 because basically the maximum goes away, and when you take expected value, each of these terms is 0. Okay, so in that case we get, let's for a second, I'm going to change notation, but for a second, let's call this R, will be 0. And now let's suppose at the opposite extreme that, S is shattered by the hypotheses, that this is a shattered set of points. Okay, so I didn't mean to write that. So S is shattered by H. By the way, it can never be negative, so this is the smallest possible value. So if S is shattered by H, then what would this be? Yeah? Okay, why?
You can find H that makes all the terms in the sum positive, so you get M in the sum and then...
Right, so for any labeling, there's some H that exactly matches that labeling. That's exactly what it means for it to be shattered. So these terms will always be exactly 1 when they're maximized. And so when you take expected value, you still get 1, which is the maximum it can take. Okay, so there are two extremes to give you some idea of how it's measuring complexity of the hypotheses that we're working with. Okay, so this is going to be called Rademacher complexity. And we're going to see that we can prove bounds using Rademacher complexity and that they subsume everything that we've talked about so far. So I guess I'm out of time. So this afternoon, we will continue talking about that.